So let's look at a very important topic of lung compliance. I will start by using the Hooke's law analogy. You remember from high school that anytime you have a spring or a string or any elastic material, there are two points here. If you stretch the material, it's going to recoil with a force. So the longer the stretch, the greater the recoil force. So what we can clearly see is that the recoil force is directly proportional to the length of extension until you reach the elastic limit. I think you discussed this in high school physics. So basically we can say that the stretching force and the extension are directly related. You remember we mentioned earlier that because of tissue elastic factors like elastin and surface tension, the lungs have elastic or has recoil properties. Anytime the lung is stretched, it's going to recoil back. There is a concept we call compliance. And basically what compliance seeks to do is to assess the stretchability of the lungs, the ability to stretch the lungs. Hooke's law is based on mechanical systems, so the graph is purely a straight line, but the principle is primarily the same. When you look at the lungs, we can say that when you apply a greater stretching force, you attain a bigger lung volume. Remember from the earlier lectures, we said that the stretching force of the lung, or the force that causes the lung to distend, is the transpulmonary pressure, if you remember. And by definition, we mentioned that the transpulmonary pressure is a difference between the alveolar pressure or intrapulmonary pressure and the intrapleural pressure. So transpulmonary pressure basically is alveolar pressure minus the pleural pressure. And we said that the transpulmonary pressure is a primary determinant of lung volume. In other words, the bigger the transpulmonary pressure, the bigger the lung volume. So it's similar to Hooke's law. When you apply a bigger distending force, then you have a bigger length of extension, or you have a bigger volume of the lung. So we can say that the lung volume you attain during inspiration is proportional to the amount of transpulmonary pressure you apply. If you plot a graph of lung volume on the y-axis versus the transpulmonary pressure or the intrapleural pressure on the x-axis, you get what we call the compliance curve. And how do you get a compliance? You get a compliance by just finding the gradient of the curve. Remember from high school, the gradient is a change in the y-axis divided by the change in the x-axis. Therefore, in this case, the lung compliance becomes the change in the lung volume divided by the change in the distending pressure. And in this case, the distending pressure is the transpulmonary pressure. In some textbooks, they will replace the transpulmonary pressure with the negative intrapleural pressure. So either is okay. Bottom line is, if you want to determine the compliance of the lung, you plot a graph of the lung volume, the change in lung volume. Then you also plot that on the y-axis. Then you have the distending pressure, which is the transpulmonary pressure, on the x-axis. Then when you find a gradient of this line, you get a variable called compliance. So this is a mathematical model. In a Hooke's law, the model assumes the constant of elasticity, but here the constant of elasticity, which is or the measure of the stretchability, is what we call the compliance of the lung. So this is just a mathematical model. Let's look at in real life what we define as compliance in simple plain terms. Yeah, so this diagram further illustrates the same concept. You have lung volume on the vertical axis and the transpulmonary pressure on the horizontal axis. Then you realize that as the transpulmonary pressure increases, the lung volume increases. But the relationship is not a linear one. We'll look at the shape in the next couple of slides. The relationship is not linear. However, it is clear that as the transpulmonary pressure increases, the lung volume increases. So initially, you have this lung volume at this transpulmonary pressure. As the transpulmonary pressure increases to this point, you have a bigger lung volume. How do you determine? So this is just about stretch. So you can see that the lungs are being stretched. What is the evidence of stretch? You can see the lung volume is increasing. Just before I emphasize on the stretch, you can recall that there are two factors that promote recoil. And the two factors are the elastic tissues or the elastin and the surface tension. And the surface tension is the greater of the two forces. At any given time, it accounts for greater than 50% of the total elastic forces in the lungs. The recoil is the opposite of stretch. Stretch compliance is a measure of stretchability. Recoil is the ability, from the name, the ability of something which is stretched to get back to the collapsed state. The way we mathematically compute the stretchability of the lung is to find a change in the lung volume versus the change in the transpulmonary pressure. So for example, let me give you this illustration. If you apply a transpulmonary pressure of 10, let's assume you apply a stretching pressure of 10 or a stretching force of 10, and you achieve a lung volume of 50. Case 1, you apply a stretching force of 10, you achieve a lung volume of 50. Then we can say the compliance is the change in volume, which is 50, over the change in stretch, which is 10. So you get 5. Case 2, you apply a stretching force of 10, but you achieve a lung volume of 80. You achieve a change in lung volume of 80. Therefore, the compliance becomes 80 over 10, which is 8. You can easily realize that the compliance in the second situation is higher than the compliance in the first situation. 8 versus 5. And the implication was that, or the cause of this was that when we applied a stretching force of 10 in either case, we achieved a bigger lung volume in the second case. The change in lung volume in the second case was 80. So if you find a change in lung volume, and that change in lung volume is bigger for a given descending force, then we say the lung is more compliant. In other words, a more compliant lung is a lung which can descend or which can increase in volume more, or which can experience a greater increase in lung volume when you apply a given stretching force. i.e. stretchability, aka compliance, is how much lung volume you can achieve for a given change in transpulmonary pressure. In summary, the lung is an elastic tissue, or it acts as an elastic tissue. Elasticity is based on two main factors: the elastic tissues in the lungs and surface tension forces. Surface tension forces are the greater of the two, or is the greater of the two. The elastic behavior is not linear. Lung compliance is the opposite of elasticity. The bigger the elasticity, remember, elasticity deals with recoil, and lung compliance deals with stretch. So if you have more recoil or more elasticity, you have less lung compliance. put in context, we'll look at it very soon, but the pediatric lung or the lung of a child has a greater elasticity. Because of that, we say it is less compliant. The opposite can be found in the adult situation. This diagram seeks to further highlight the mathematical concept of lung compliance. So you can see here that there is a change in lung volume, and you can also see that there is a descending pressure. In this graph, the descending pressure is the negative intrapleural pressure. And all you are doing is that you are finding the change in volume over the change in pressure. That change in volume over the change in pressure becomes a slope of the graph. And that slope represents compliance. Remember, the compliance is change in volume or change in descending pressure. Therefore, when you have a compliance curve, the slope of the compliance curve represents compliance. What is a compliance curve? Graph of change in volume over change in descending pressure. The slope of that curve represents the compliance. The greater the slope, the greater the lung compliance. This slide just talks about what we have mentioned earlier. Lung compliance is a change in the lung volume per unit change in the descending pressure. Lung compliance is a gradient of the curve of lung volume plotted on the vertical axis against a stretching pressure, transpulmonary pressure, intrapleural pressure on the x-axis or the horizontal axis. Lung compliance is a measure of the stretchability or the distensibility of the lungs. It is not the measure of recoil. The measure of recoil is elasticity. Lung compliance and elasticity are opposite. A compliant lung is a less stiff lung. It's a lung which can easily inflate. A lung which is distensible. A less compliant lung is a stiff lung. We now look at the detail of the lung compliance curve. Remember this experiment. You remember if we have a balloon, in this case representing a lung, in a vacuum container, or let's say a wash bottle connected to a vacuum pump. When you take air out of this chamber, you drop the pressure outside here, so the pressure here becomes more negative. Because it becomes more negative, the pressure within the lung becomes greater than the pressure outside the lung, and that causes it to stretch. So anytime you take air out of the chamber, the lungs stretch. Why does the lung stretch? When you are taking air out of the chamber, you are making the intrapleural pressure more negative. When the intrapleural pressure becomes more negative, the transpulmonary pressure becomes bigger, and the transpulmonary pressure is a descending pressure. So you can see clearly from this diagram that as the intrapleural pressure becomes more negative, the lung volume increases. By the way, there are two arms of this curve. The first arm is the inspiratory arm, and the second arm is expiration. So basically what you do in inspiration is that from here to here, you make the intrapleural pressure more negative. We highlighted that earlier. So during inspiration, we make the intrapleural pressure more negative. However, during expiration, the intrapleural pressure is made less negative. There are quite a number of observations from this curve, important for basic physiology for medical students. Point number one, that the compliance curve is not linear. It is a curve. You can see that, you remember we said that the gradient of the compliance curve or the gradient of the graph of volume against pressure is the compliance. The bigger the gradient, the bigger the compliance. So let me do an illustration before I come back here. So for example, we'll look at this diagram very soon. You look at three curves. Gradient is how steep a graph is. So you can see that if this is the ideal graph or the normal graph, this is less steep. Because it's less steep, it has a lower compliance. It's steeper, so it has a greater compliance. So when we talk about gradients, we talk about the steepness or the slope, how steep curve is. So if the gradient is higher, it's steeper. If the gradient is lower, it's less. We now come back to what we were doing earlier. So you can see that we mentioned that a graph is not a straight line. The implication of a graph not being a straight line is that the gradients vary from place to place. So there are 2 points of note. The gradient of a compliance curve is greatest in the mid segment of the curve. So we have the greatest gradient in the mid segment. At the start, the gradient is not fantastic. At the end, the gradient is poor. But somewhere in the middle, we have the highest gradient. So during inflation of the lungs, during inspiration, you have the best inflation, you have the best compliance, you have the best distensibility in the mid segment of inspiration. The same thing can be said about expiration. So compliance is least towards the end of inspiration. That's the first point. The second point is that the compliance curve doesn't start from a zero lung volume. The reason why the compliance curve doesn't start from a zero lung volume is that we have established that at any given point, there will be a volume of air in the lung called the residual volume. So you always start from the residual volume, and you have an increase in the lung volume until you achieve your total lung capacity. So take note that the compliance curve doesn't start from zero, it starts from a certain lung volume, reflective of the residual volume. 3, you can clearly see that the inspiratory loop is different from the pathway of the expiratory. So this is a loop, the inspiratory segment follows a different pathway compared to the expiratory segment. So the inspiratory segment goes like this. You'd have expected that naturally, if the inspiratory segment goes like this, and the expiratory segment will follow it exactly in the reverse. But that's not what we observe. The inspiratory segment goes like this, but the expiratory segment follows in a different path. Anytime you have such a phenomenon in general physics, especially electromagnetic fields, we call it hysteresis. So we say that the lung inflation curve exhibits hysteresis. These are therefore the features of the lung inflation curve. First of all, the curve doesn't start from a zero lung volume because of residual volume. Next, the curve is not linear. It has a smaller slope at the start, a fantastic slope in the middle, and at the end of the curve, it has a poor slope. So it is difficult to start to inflate the lungs, but once inflation has started in the mid segment, inflation is very easy. You know about this when anytime you want to blow a balloon. And we also do know that at the end, it's very difficult to further inflate the balloon because you sort of achieve almost a total lung capacity or the total capacity of the balloon. So at the tail end, compliance drops. Next, the curve exhibits hysteresis. Hysteresis, the inspiratory limb follows a different pathway or a trajectory compared with the expiratory limb. High lung compliance versus low lung compliance. Compliance is the gradient of the volume pressure curve. So the greater the gradient, the greater the lung compliance. If this is normal compliance, then this has a lower gradient, so a lower compliance. This has a higher slope or a higher compliance. We are not doing pathology, but later on in your rotations, we'll learn that there is a condition called lung fibrosis, where you have stiffening of the lungs. So because the lungs are stiff, they are not very compliant. So the compliance drop markedly. And we also have another condition called emphysema. In emphysema, the amount of elastic tissues in the alveoli drops. Remember, elastic tissues are supposed to cause the lungs to recoil back after stretch. So those recoil forces oppose the stretchability of the lung. Therefore, if you have emphysema, you don't have those recoil materials, you don't have those elastic materials. Recall drops, and when recall drops, compliance increases. Compliance is the opposite of elasticity. You need to take note that the pediatric lung is less compliant. The reason why it's less compliant is that it's more elastic. There are a lot of fresh elastic tissues in the lungs. So there is a tendency for it to recoil than to stretch. With aging, there is a tendency of the lung to stretch in the natural position compared with recoil. There are some other conditions here which are not important at this level because we've not done a significant amount of we've not covered a lot of grounds in pathology yet. But later on we'll learn that if you have a hydrothorax, for example, fluid collection in the pleural space, pleural effusion, any other collection, it also drops the compliance. There is a condition called acute respiratory distress syndrome where the lung compliance further drops. Abdominal, anything that pumps something to the abdomen, either a fluid or a gas, in this case a gas, can also drop the compliance of the lung because of the mechanical restriction. Atelectasis, alveolar collapse, the compliance of the lungs drops. There are some problems of high lung compliance and low lung compliance. Remember, if the compliance of the lung is low, it's very difficult to distend it. It means that anytime you are inspiring, anytime you want to take in a breath, you need a lot of effort to distend the lung. So the work of breathing increases. Because the work of breathing increases, it makes it difficult to achieve a successful respiration. You easily get tired with inspiration. So one of the big problems of low lung compliance is that you need more energy, you need more effort to distend the lungs, and that increases the work of breathing. There is also a problem with very high lung compliance. The problem with the high lung compliance is that if the lungs are highly compliant and less elastic, then recoil becomes a problem. Now, you need that recoil to exhale gases. So if you have problems with recoil, one of the implications is that you are going to trap gases in the alveoli. It becomes a bit difficult to achieve normal expiration. I'll probably skip this scale because it is a repetition of the concept we have discussed. Before we conclude and come to the practical segment of the course, take note that there are some regional differences in the lung compliance during inspiration. If you are in the upright position, then we can say that the lungs are just a second. Let me just answer this call. Yeah, so we had 3 questions from the students. Question number 1 is, can we simplify the concept of compliance to the layperson? So it's simple. You have a balloon. So when you blow the balloon is becoming bigger. When it's becoming bigger, we say you are stretching. The balloon is being stretched. It's becoming bigger. So that is a measure of compliance. Compliance is stretch. It's becoming bigger. It's like you have an elastic band. When you apply some force, you can stretch it. When it's becoming longer, that is compliance, stretchability, distensibility. When you leave the stretched rubber band or you leave the balloon alone, it's going to shrink, it's going to recoil. That shrink or recoil is what we call recoil or elasticity. So compliance and elasticity are opposite to each other. While compliance makes the balloon bigger, elastic recoil makes it smaller. Now to the layperson. Yeah. The second thing is about the curves. Remember that when it comes to the curves, it's pretty much straightforward. If you want to measure compliance mathematically. So what we have just discussed is a layman's explanation. But there should be a way to compute or to measure the magnitude of the curves. How do you measure the magnitude of the curves? You plot a graph of change in lung volume on the y-axis versus a descending pressure. The descending pressure can be intrapleural pressure or transpulmonary pressure on the x-axis. Volume y-axis, descending pressure x-axis. Volume vertical axis, descending pressure horizontal axis. Then you can find the gradient, the slope. The slope is going to be the change in volume divided by the change in pressure. That change in volume by the change in pressure represents the compliance. So the bigger the slope, the bigger the lung compliance. Someone also wanted to confirm whether lung compliance will increase in obesity, and I said that's absolutely correct. There are specific mechanisms for decreasing lung compliance in obesity, but the obvious one is because of the mechanical effect, mechanical restriction of lung movement, especially in abdominal obesity. So the student is correct. We can conclude with the final slide, change in regional differences in lung compliance during inflation or during inspiration. Please take notes that remember we said one of the principles of pressure is in high school is that pressure increases with depth. Pressure increases with depth. So from top to bottom, pressure increases. You probably remember the high school experiment. You have a tank here, and you make 3 holes here. Water is going to gush out of the top hole with less pressure, so the pathway of the water will follow probably something like this. And the middle one will gush out with some level of pressure, probably something like this. And the lower one is going to come out very forcefully with a lot of pressure, probably something like this. So we see that the deeper you go, the greater the pressure. So from the apex to the base, there's the apex of the lung and there's a base of the lung. From the apex to the base, we can say that the intrapleural pressure increases. When we say something is increasing, it means it becomes less negative. So for example, at the apex, the intrapleural pressure is minus 10 centimeters of water. But at the base, you have the intrapleural pressure to be around minus 2.5 centimeters of water. You remember, we mentioned that we use an average intrapleural pressure of around minus 5 centimeters of water. That's an average. But technically speaking, the intrapleural pressure varies from apex to base. Because of the variation of the intrapleural pressure, we can also say that the transpulmonary pressure also varies from apex to the base. So let's measure the transpulmonary pressure at the apex and at the base. The transpulmonary pressure is alveolar pressure, which is 0, minus the intrapleural pressure. At the base, it will be 0 minus 2.5. So you get a positive 2.5. At the apex, the transpulmonary pressure becomes 0 minus 10. So 10 centimeters of water. Which of the two transpulmonary pressures is bigger? Obviously, the minus 10 centimeters of water. So we can say that the descending pressure, the transpulmonary pressure, is higher at the apex than at the base at functional residual capacity. Functional residual capacity is when you are at the end expiratory level. You are not taking in any breath. You are about to inspire. At the point where you are about to start inspiration, the transpulmonary pressure is bigger at the apex than at the base. 10 versus 2.5. You remember that we said that the alveolar volume depends on the transpulmonary pressure. If the alveolar volume depends on the transpulmonary pressure, then it means the bigger the transpulmonary pressure, the bigger the starting alveolar volume. So before you take in any breath, because the transpulmonary pressure is bigger at the apex, then the alveoli at the apex are more distended. They are bigger to start with, because the alveolar volume is bigger than is dependent on the transpulmonary pressure, and the starting transpulmonary pressure is bigger at the apex. The same way, the alveolar volume will be smaller at the base. So imagine you have 2 sets of alveoli before you start inhalation, before you start inspiration. You have 2 sets of alveoli. One is already distended, the other is less distended. And you are about to inhale or inspire. Which of the two will have a greater potential to descend further? Remember the apex, the alveoli are already fairly distended. Here they are smaller, they are not distended significantly. Now you want to inhale. Which of the two alveoli will have a greater tendency to distend during inspiration? Obviously, you are right. It will be the alveoli at the base because they are smaller to start with. They are not distended at the start, so they have a greater capacity, a greater tendency to stretch. So bottom line is that in the upright position, the lung compliance or the change in lung volume is bigger at the base than at the apex. We'll return back to this later, where we'll learn that pulmonary ventilation, for example, will be bigger at the base compared to the apex. Practical applications. Let's look at the concept of the Laplace law. So we will further look at some of the factors that affect surface tension. We'll probably delve a bit deeper later in the course, but in this introductory lecture, I'll seek to give you the basic concept. Remember, we used the model of the sphere to explain surface tension. We said that if you distend the spherical object, there will be a tendency for the spherical object to collapse. Then the force that promotes the collapse or the shrinkage acts towards the center. These forces can be represented as surface tension. And you know clearly that the bigger the sphere or the more you inflate the balloon, the bigger the tendency to collapse. In other words, the surface tension forces becomes bigger with increasing radius. So what we say here is that when the radius is bigger, the surface tension forces will be bigger. Great. So let's have a quick recap. We said that anytime you have a spherical object and you inflate it, there is going to be a force or some tension on the surface, right? So that tension is what we call surface tension. We'll learn very soon that anytime there is an air-fluid interface, you develop surface tension. So you just picture this one as the surface tension, the tension on the surface of the sphere. Now surface tension acts, it exerts a force or a pressure, and the function of the pressure or the force is to collapse the alveoli. So the bigger the surface tension, the bigger the pressure inside the spherical object to collapse the alveoli. There are some implications to consider here. The first one is that if we allow the surface tension to prevail as it is, then there will generally be the opposition to deliberately prevent the alveoli from distending, because anytime it distends, the surface tension will increase. And when the surface tension increases, it's going to cause the alveoli to shrink. So there will be a deliberate, there's going to be a deliberate process to prevent the alveoli from expanding. Anytime the surface tension is high, the alveoli are going to collapse. So what do? If you want to prevent these alveoli from collapsing, then you need to apply something that will oppose the surface tension. What opposes the surface tension, we are going to call pulmonary surfactant or surfactant. Before we do that, the Laplace law is pretty much straightforward. It just tells us that before the law, we just know that the surface tension generally acts to collapse the lungs. Then the tension that develops on the surface of a sphere is proportional to the radius. So there are two ways of looking at it. And an easier one is that the tension that develops on the surface is proportional to the radius. The second way to look at it is to make P the subject. If you make P the subject, then you realize that P will be proportional to T over R. In other words, the pressure you develop in a sphere is proportional to the surface tension or the tension on the surface. Either is correct. But in this lecture, I'll focus on the relationship between T and R. The bigger the radius, the bigger the surface tension. And the bigger the surface tension, the greater the tendency for the sphere to collapse. Therefore, anytime you have surface tension, the surface tension will act to collapse the alveoli. You wouldn't want to do that as a physiologist. This is a natural state of the lungs. You have a lot of surface tension, and the surface tension will want to collapse the alveoli. So the body will need to do something to prevent these from collapsing, to prevent the alveoli from collapsing. What does it do? The body, especially type 2 pneumocytes, alveolar epithelial cells type 2, will synthesize a chemical called pulmonary surfactant. And the role of the pulmonary surfactant is to drop the surface tension. When you drop the surface tension, you drop the tendency of the alveoli to collapse, and it becomes easier for the alveoli to distend during inspiration. So take note that surface tension acts to collapse the lung. Surface tension, surfactant decreases surface tension. Because surfactant decreases surface tension, surfactant aids alveolar expansion during inspiration. Remember that pulmonary surfactant is produced by type 2 alveolar cells, and they typically line the alveoli. They have a short half-life, so they must constantly be produced. There is one clinical application. In your embryology course, if you remember, we said that pulmonary maturation, lung maturation in the fetus is complete by 36 weeks. Generally, between 24 to 35 weeks, we have a fetal synthesis of pulmonary surfactant. So at the end of the 35th week or by 36 weeks, we can assume that the lungs of the fetus is fully matured. But how do we, there are some individual variations anytime it comes to physiology. So there should be an objective way to know whether the lung of the fetus is matured or not. To do this, you measure what we call the lecithin single myelin ratio. So there are a number of amniotic fluid tests we can perform. We'll focus on just two. There is a test called a lecithin single myelin ratio. When you run a lecithin single myelin ratio and you get greater than 2:1, then we can say that the levels of pulmonary surfactant are adequate. Now, there are some other tests apart from the lecithin single myelin ratio. So the magic number you have to keep in your head is 2:1 or 2. If the LS ratio is greater than 2, it reflects mature levels of pulmonary surfactant. There are some other tests we can also do to assess the maturity or the maturity of the lung. One of them is the surfactant albumin ratio. If the surfactant albumin ratio is less than 35, it's highly indicative of immature lungs. If it's greater than 55, it indicates mature lungs, adequate levels of pulmonary surfactant. Between 35 to 55, we are not too sure. We now look at what we call the neonatal respiratory distress syndrome. If, for example, we need to perform the delivery of a fetus before maturation, we said that the fetal lungs are matured after 36 weeks. So, for example, you have COVID-19 in a pregnant woman who is 34 weeks or 33 weeks, and the fetus is at risk, and the physicians decide to take a decision to do a cesarean section, or you have a hypertensive condition in pregnancy, anything that is a threat to the fetus or the mother, and the obstetricians or the doctors in charge decides to deliver the fetus ahead of time. Let's say you have a fetus 33 weeks, you need to have a cesarean section to deliver the fetus. Remember that at that time, the chance of lung maturation is very low. It's likely the lungs are not well matured. If they are not well matured, it means you are not going to have adequate levels of pulmonary surfactant. Remember, surfactant is supposed to reduce surface tension. So if you don't have good levels of pulmonary surfactant, it means there will be high surface tension in the lungs. If you have high surface tension in the lungs, the first thing is that you are going to have alveolar collapse. That is called atelectasis. 2, it will be difficult to reinflate the lungs during inspiration. Remember that we said that for the lungs to be compliant, then you should have less recoil forces. And one of the recoil forces is surface tension. If the surface tension is very high, the lungs will have a general tendency to shrink. So lung compliance becomes lower. It becomes difficult to inflate the lungs during inspiration. So we see that the work of breathing increases. Because of that, because of these two factors, there is something called ventilation perfusion mismatch, which is a focus of our next 2 lectures. There's going to be a ventilation perfusion mismatch, and because of that, you are going to have hypoxemia. Hypoxemia is reduced oxygen partial pressure in the arterial blood. The amount of oxygen, the partial pressure of oxygen in the arterial blood is going to drop because of these problems. Remember, the alveoli, the function alveolus is critical for adequate pulmonary gas exchange, which will determine how much oxygen is in the arterial blood. Because these 2 are defective, or these 3 are defective, there will be a tendency for you to develop hypoxemia. In addition to alveolar collapse, difficulty in inflating the lungs, ventilation perfusion mismatch, there is also a tendency for non-cardiogenic pulmonary edema or alveolar edema. And I'll explain this one under the pulmonary circulation lecture. But in essence, when the alveoli collapse, there is a greater tendency for it to resorb fluid from the pulmonary capillaries. So there's going to be edema, there is going to be fluid collection in some of the alveolar cavities. So anytime you have a preterm baby, then there is a chance that they are going to be hypoxemic. There is a chance that they are going to have respiratory problems. And the reason why they have respiratory problems is that their lungs are not matured. They don't produce adequate levels of pulmonary surfactants because of that surface tension is too high in the lungs. There is alveolar collapse, difficulty in inflating the lungs, ventilation perfusion mismatch, non-cardiogenic pulmonary edema. How do we help this individual? Before we help this individual, we should talk about how we can prevent the situation. So if there is a need to deliver a fetus, by all means, as physicians, there is a technique we use to artificially mature the lungs. And one of the things you can do is to administer steroids to the mother. So steroids are a group of drugs, and one of the things they do is that they promote the maturation of type 2 alveolar cells. So when you administer steroids to the mother, for example, betamethasone, they cross the placenta, gets into the fetus, they promote the proliferation and maturation of type 2 pneumocytes, and the amount of pulmonary surfactant you produce in this fetus increases. So that helps to reduce the tendency of alveolar collapse and all the attendant pulmonary complications. So typically, we administer the steroids to the mother about at least 12 hours, preferably 48 hours before delivery or before the cesarean section. And when you do that, there is a significant improvement in neonatal pulmonary maturation. If you are not able to do that, or you do that and it doesn't work, then what you need to do is that you have to administer pulmonary surfactant to the neonate, the born unit, the preterm unit, or you can artificially ventilate. There is another technique called extracorporeal membrane oxygenation, which is we focus on this in the graduate class. So ECMO is not going to be our focus in the basic pulmonary physiology course. Chest wall compliance will be handled in a tutorial session, but key points of note is I remember when we were looking at say intrapleural pressure, we talked about the opposite direction of the movement of the lungs and the chest wall at FRC. One tends to recoil inwards, the other tends to move outward. The chest wall also has a compliance. Compliance is a measure of the extensibility, if you remember. But the big point here, which I want you to know, is that because of the way they act, they don't act in unison. Because of that, if you want to find the total compliance of the respiratory system, it's not a simple addition of lung compliance and chest wall compliance. It's like you have a resistors combined in, I think, parallel or so. So 1 over the total pulmonary compliance is the same as 1 over the lung compliance plus 1 over the chest wall compliance. So as I mentioned, I'm going to focus on the chest wall compliance later. Any questions?